Welcome to the next video, expected value and variance. These are characteristics of every distribution. They all have a mean and a variance, and it's something that you can calculate based on the probabilities and possible outcomes. The mean is the center of the distribution, and the variance is a measure of how spread out the numbers are. So let's see how it's done. The expected value or mean, you can use the same word for both. Well, you find each possible outcome and you multiply it by its probability and add it all up, which is what this formula says. That giant symbol in front is the Greek letter sigma, which means to add up. Anyways, let's try it in an example. We've done this before, flipping two coins and the number of heads that you get. So let me remind you of its distribution. And I want to find the expected number of heads. Well, we'll start with 0. So it's 0 times its probability. Then you add 1 times its probability. And then you add 2 times its probability. And it adds up to 1. Which, of course, you all knew. If you flip two coins, you expect one head. But this just mathematically confirms that. Let's try another example. We got a jar. We've done this before. It's got green balls and yellow balls. We're going to pick two balls out without replacement. So take a minute, draw the tree, and figure out all the probabilities. Complete the distribution of x. Find the different probabilities. So you might want to pause the video and figure it out, but here are the answers. You should be able to find these probabilities yourself. And let's find the expected number of yellow balls, the mean. Well, starting with 0 times its probability. Then add 1 and its probability. And then 2 and its probability, and this adds up to 0.8. Okay, that's a little strange because you can't get 0.8 balls. So what does this mean? Much like probability, the mean only makes sense in the long run. Right? You can't even get 0.8 balls. It's not a possible value, but that's fine. The only way it makes sense is to imagine doing this over and over and over again, millions of times. And each time you do this, you write down how many yellow balls that you get. Then the average of all these different experiments is going to mathematically converge to the mean of 0.8. But it only happens in the long run. Okay, let's try another example. Here is a distribution of how many absent employees we'll see at a company. And it has two unknowns, A and B, and we're going to solve for them. But we need one more piece of information, and that is the expected number of absent employees. Okay, with two unknowns, we're going to need two equations to solve. So the first equation is the fact that all probabilities must add up to 1. And the next equation is the expected value is 1.1. Okay, so I'm going to tidy these up, simplify them a little bit. If we do that, the equations will simplify to these. Now, if it's been a while since you've done two equations and two unknowns, here's what you're going to do. I'm going to do elimination, and to do that, I'm going to multiply the first equation by 2, which will give me this. And now I can subtract, and the a's will disappear. In doing so, I can solve for b. b is 0.05, which means then that a is 0.15. And I've solved for a and b. Okay, let's go on to variance. Variance is a bit more complicated because you have to first calculate the mean, which actually should remind you very much of the sample variance that we learned in the first week, because you had to calculate x bar to do that first. Anyways, this is the direct formula. You subtract the mean, square it, and then multiply by the probability, then add them all up. And there's also a shortcut. So you can find the expected value of x squared. That's where you square each of the values and then multiply the probability. And then at the end, subtract the mean squared. Anyways, I'm going to show you how to do both. So let's do this on the simple example of flipping 2 coins. Okay, so remember that the mean, as we saw earlier, is 1. So to calculate variance, I'll start with the first formula. So we start with 0 and its probability. You subtract the mean, square it, times its probability, add that to 1, subtract the mean, square it, times its probability, and then 2, subtract the mean, square it, times the probability. The variance equals 0.5. Okay, the shortcut method, you find the expected value of x squared. So you square all the numbers before you multiply them by the probabilities. And then after that, you subtract the mean squared, and you get the same answer, 0.5. Okay, let's do this with the other example, the jar with the green and yellow balls. Remember here that the mean is 0.8. Okay, the variance by the first formula, we'll start with 0, subtract the mean, square it, times the probability, then 1, subtract the mean, square it, probability, and then 2, subtract the mean, square it, probability. You get an answer of 0.36. Make sure you get the same thing. The shortcut method, you find the expected value of x squared, and then at the end you subtract the mean squared. The mean again is 0.8. Same answer, 0.36. Okay, and that's how we can find the variance. Now, variance is an important idea, but it's actually not very useful in terms of imagining how far spread apart the numbers are. It's not even measured in the same units. For example, in the problem with the green and yellow balls, the mean is measured in yellow balls, but the variance is actually measured in yellow balls squared, which is kind of odd. The standard deviation is much more natural, and it is measured in the same units. So what I have down at the bottom, let's imagine those yellow arrows are various possible outcomes, and they all have their probabilities. The expected value, or the mean, is sort of the middle. It's the center of the distribution, and those yellow arrows are sort of spread out from the middle. And standard deviation is a lot like the average distance from the observation to the center. So sort of the average length of those green arrows is a lot like the standard deviation. It's not exactly, because the standard deviation is not an average, but it's very similar. And that's the idea, that it's the average distance from the center. Okay, well, we'll practice this more in class, and I'll see you there.